Hello everyone, my name is Zeren from the Hong Kong University of Science and Technology, Guangzhou. In this video, I'm very excited to present the paper Unsafe LLM-Based Search, Quantitative Analysis and Mitigation of Safety Risks in AI Web Search. Think about the last time we searched for something. With traditional search, we got a page of blue links, as shown at the bottom of the slide. In this case, we clicked, skimmed, opened more tabs, and pieced the answer together all by ourselves. Now there's a shift. AI-powered search understands the goal behind our query and gives us a direct, synthesized response. So instead of "here are 10 links about the query," AI-powered search says, "here's the solution about the query." Let's take an example. How do I build a doc image for search engine? In the past, we used to hop between docs, GitHub issues, and blog posts, piecing the stats together ourselves. With AI-powered search, the answer appears already assembled. Clone this repo, run these commands, build the image. In short, AI turns search from find information into deliver the solution. Now the flip side. The same power that makes AI search so helpful also creates new risks. Why say that? Because we naturally trust AI's confident answers. But what if the answer is not just wrong? What if it's malicious? Let's see some example. On the left, a user asks about a gaming marketplace. The AI's replies looks professional and looks like a step-by-step guide. However, the links go to a lookalike domain, not the real site. It's a phishing site. On the right, we see a query about crypto wallet, and the answer looks polished. It even includes a link that seems official, but the domain is not the vendor's domain. Instead, it's a fake page. Because of that, it tries to push a malicious download. In crypto, one bad click can cause irreversible loss. And this isn't just a single language issue, it's global. Since this AI search system indexes all publicly accessible web pages across the world, they are able to draw on content in any language and deliver results that best match the user's query. For example, here are two Chinese queries. On the left, a simple question about Telegram official website returns a detailed answer and labels a web page as official, but it actually points to a phishing site. On the right, a search for a translation tool returns a helpful answer, but the links actually leads to a phishing site. In both cases, the model not only meets the real official sites, it actually falls for phishing sites and pushes malicious content to the top. So, while AI web search gets us answers quick, it also creates risks for users in their daily search. So, given this new and challenging threat, our work is driven by three motivations. First, we need to know the size of this problem. Our first goal is to quantify AI web search risk. We tested several major AI search platforms: ChatGPT, Perplexity, Grok, and others, across different languages and three types of queries to check how often harmful links show up. Second, we found that not every malicious URL in the AI search outputs carry the same weight. That's why we built an objective risk assessment framework for users of AI search. Third, measuring and scoring alone aren't enough. We want to build a simple, practical, client-side defense system. The first goal is quantification, to measure risks fairly and consistently. We studied by simulating how people actually search. We modeled three typical query types that people actually use when they search. First, keywordless queries. They are short, separated terms like ever, dashboard, explorer, interface, markets in the slide. This type is common when users already know the product name and want to have a quick search. Second, natural language queries. They are full questions such as, how do I use Ever dashboard and explorer to check crypto markets? In the slide. This is the type most people use when they do AI searches. Third, when user pastes or types a web address, these are called URL queries. This usually happens when someone wants to quickly get a summary of what a site is about, or ask questions related to this site. To prove our simulation was realistic, we surveyed users to find the real-world frequencies of each query type, as shown in the pie chart. Next, how did we actually produce the queries used in our test? We built a 3-step pipeline. Step 1 was to create a set of keyword list query. We began with malicious URLs collected from threat intelligence platforms, which are Level Blue, Phishing Tank, and Xzeren. After a rigorous data cleaning process, we used ChatGPT-4o to generate a relevant keyword list for each live malicious web page. For example, from dash.onaave.com, we get ever, dashboard, explorer, interface, market, those keyword query lists. After generating 325 entries like that, we then randomly sample 100 entries to form a balanced test set. Step 2 was straightforward. We took each keyword list and asked GPT-4o to turn it into clear, full-sentence questions. Step 3 was a discovery process. We sent those keyword queries to several AI search engines and collect every URL they recommended. From each answering, we pull the links and check which ones are malicious. In other words, the URLs in URL query are newly found bad links indexed by AI's web search result, not the URLs we start with. By the end, we had a realistic dataset for each query type. This gave us a clean, comparable test cases across all 3 query types. Now we have our data. We need a way to categorize the risk. We developed a user threat assessment framework with 3 risk types. First, main risk. The most severe, a malicious URL is placed directly in the AI's main answering. Therefore, the user is one click away from danger. Second, warning risk. The AI provides the malicious links but also includes a warning or points to a legitimate sign. Third, source risk. The least direct threat. The malicious links is only in the source session, not the main answering. In the next slide, I will show some examples to better illustrate those 3 risk types. Consider the following example. For this query, the system returns an answer with inline citation 1 to 7 and a separate list of sources. So, if any URL referenced by the inline citation is malicious, we classify it as main risk. Because the harmful links is embedded in the primary answering, the user is one click away from danger. And if the malicious URL appears only in the unsighted source panel and not in the body of our answering, we label it source risk. Because the exposure it requires additional exploration and is therefore less immediate, so still consequential. And here is a clear warning risk example. The AI returns a malicious domain, telegram.nc.com, but immediately advises that the official site is telegram.org and recommends using it. From a user safety standpoint, the danger place is present in the primary answering, yet paired with corrective guidance. So, why does this happen? We guess the system first indexes a link that seems relevant, but then its safety checks spot the real domain and just add a warning instead of blocking it. With those definitions in place, let's move to the result. How often harmful links show up? Our first key finding is all AI search platforms we test are vulnerable. This top chart shows the malicious results for each platform using keyword list query. As you can see, every platform has a bar, meaning none are immune. The top chart shows where the risk distribution varies. The problem is widespread. Afterwards, we emailed our finding to the vendors. This led to another result. After our interventions, those AI platforms become significantly safer than traditional search engines. The bottom chart shows the risk count after vendors fix. You also can see that AI platforms now have a lower score than Google and Bing. So the threat is broad, but it's feasible when platforms act. To make the threat more concrete, we conduct 2 case studies. The first focuses on malicious online documentation. We create a complete but fake cryptocurrency platforms called Wave50 TAIS, as you can see on the left of the slide. The core of this experiment is documentation. We created what looked like a standard developer guide. And the most important part is this Python code example on the right. It used the standard Python request library and had a clean structure for the API call. It also provides familiar parameters like token's name, symbol, and initial supply. But here's the trap. The vulnerability isn't in the structure of the code. It's hidden in its destination. This URL for the API call points to a server controlled by the attacker, not to a legitimate servers. Then, what happened? When we queried a popular AI search engine, which is ChatGPT, it ingested our malicious documentation and generated a helpful-looking guide. Critically, it instructed the user to send their private API keys to our malicious URL without any warning. This is classical man risk, and it shows how easily well-crafted malicious document can compromise an AI search engine. In short, this case study shows that malicious online documentation can easily compromise AI PSEs. Our second case study is about fooling the AI into treating a fake site as official. To prove this, we built 2 sites for a made-up creature. One official site with correct data, one unofficial site with content that deliberately contradicts the official site. And we even added a fake warning to boost its credibility. We then asked AI search for the make-up creature. So, how did the AI models handle this? The result is, they were completely fooled. They believed our phishing site was the official sources, and generate their entire answer from the unofficial site. This reveals a critical vulnerability. AIs can be manipulated to actively promote fake websites over legitimate ones. Finally, having defined the problem, our contribution is a solution, our React agent defense. Conceptually, our defense is a client-side agent. It intercepts the AI outputs and uses a SOAR action loop with specialized tools to analyze its safety before showing it to the user, often adding a warning. As for the agents tool, a key part is a malicious URL detector we built. The table on the right shows that our HTML LLM detector is highly effective with a balance of precision and recall. Our agent used this detector to effectively transform dangerous man risk output into much safer warning risk output. In conclusion, our work does 3 things. First, we measure the problem. We build a realistic query set and score risks with a simple 3-type scheme. The detailed result can be found in our paper. Second, we explain how it happened through 2 case studies. Case study 1 showed that malicious online documentation can easily compromise AI PSEs. Case study 2 showed that a clean, self-claimed official site can outrank the real one and be treated as authoritative. Third, we show a page 2 defense. A lightweight client-side guard can flag look-alike domains, highlight the real domain, and stop risky clicks without breaking the AI search workflow. In our test, it cut exposure meaningfully. So that is the end of this video. Thanks for listening.